Good afternoon, everyone. Welcome to the webinar. My name is Inash Sheikh, and I will be your co-host today. Before we get started, please let me take a few minutes to introduce EXPLIoT. EXPLIoT is an open source framework for IoT security testing and exploitation. It is the product of our experience and expertise in IoT security. At EXPLIoT.io, we build IoT security tools and target vulnerable devices for professionals and for people who want to get into IoT security. We have cooked some amazing products in our labs. A few of them are EXPLIoT.io, an advanced hardware lab equipped with the best tools and equipment performing security evaluation of hardware and IoT devices. We also have an online store where you can find all our IoT security creation and other cybersecurity hardware. We have also coded CloudFuzz. It is a scalable and distributed fuzzing platform designed to facilitate fuzzing open and closed source application on various platforms. We have recently coded IoT Auditor. It is an IoT security compliance testing and vulnerability management platform that empowers engineers to test and analyze different attacks surfaces of the IoT ecosystem, like radio communication, firmware, hardware, IoT cloud, etc. We are sharing the community edition link on the chat box. You can also scan the code on the screen to access it. Today's webinar is on debug hacks, JTAG and SWD. JTAG and SWD are debugged peripherals for microcontroller. Attacking these ports can get sensitive data from a device. In this webinar, you will learn basic of JTAG and SWD, security issues with JTAG and SWD, finding out JTAG and SWD pins on an IoT device, and how to use EXPLIoT tools to identify debug port pins and extract data from the device. Our speaker is Mr. Yashodhan. Mr. Yashodhan is an IoT researcher and compliance manager. He will take us through IoT hardware hacking. You can read about his beautiful accomplishment on this slide. At Pio2, Mr. Yashodhan is responsible for security assessment and creating threat models for IoT products. He's also working on achieving security certifications and accreditations for the organization. His current IoT security research focuses on side channel attacks and fault injection. Now, before I hand it over to Mr. Yashodhan, I request you all to follow a few housekeeping rules. Please be on mute. If you have any questions, you can write it in the chat box. We will answer the questions in the intervals or at the end of the webinar. We will be releasing the recording of this webinar on our social channels. So make sure that you are following EXPLIoT. If not, just check the link on our chat box and follow us right away. Now, without further ado, let's get started. Mr. Yashodhan, over to you.
Sure. Thank you. Thank you, Inash. So let me share the screen. I hope that's visible.
Yes.
Okay. So welcome everyone to this particular webinar. And I know whoever are working in this domain of embedded system development part. So when you go for the debugging, the JTAG or SWD, it is really pain at some time. So here today the agenda of that, like though we use it for the debugging purpose or possibly the programming your firmware to your microcontroller, eventually there are certain security issues where people can, if you get a physical access of your device, can get into some of the important registers or the firmware of your microcontroller as well. So today's agenda is to discuss about the JTAG and SWD attacks. So how we'll go is basically understand the protocols, the very basic protocols, because the details of protocol is not a scope of here. And then we'll see what are the different attacks that has happened on these particular debug ports in the past. And I'll be then showing a couple of videos that we have recorded in our lab, how we can do such attacks like finding the pins on the board or then extracting the firmware or reflashing the malicious code, how we can do that. So first of all, we'll start with the JTAG part. I will complete the JTAG. I'll show a couple of videos, the hands-on videos with the JTAG part. Post to that, I'll discuss the SWD and a video on the SWD. So this will be the flow of our discussion. So when we start the JTAG part, right? So JTAG, as we know, the NOAM is basically Joint Test Action Group, and it is basically a debug protocol. And why it is needed, the reason why it was discovered is like when you go for a very high production range where you have a number of devices, a few of the thousands of the devices that in the production, and you want to test few things. Now, as the challenge happened is like over a period of time, your the devices, because of the miniaturization, the complexity of devices has increased, as well as your design has shortened. The scale of the your system of the embedded systems has been reduced to the significant size. Now, to directly access such ports, right? So we have the UART port, we have different ports over there. But when you go to the specific to the debug part, right, we need to have a kind of a stateful protocol, which actually JTAG is. So what the basic thing that JTAG is looking for is like about the test access port, which basically interacts as a debug port, and eventually it has an access to the test registers that inbuilt your system, as well as you can actually play with the chip logics over there. So this is what it is. And the most important, it's a stateful protocol, meaning it has implemented the finite state machine over there, right? So state by state, the bit by bit, we are basically trying to decode or debug what are the things over there. Right? So it is not exactly similar to what we do in a software debugging. It is a bit different when we go to the actual JTAG debugging part over there. So as I discussed about that, the reason why we go for a JTAG is as we have very less amount of the size of the device is getting reduced, and you have a huge number of production devices to be tested during each pipeline when you start designing the product in the delivery of the product. So JTAG is much efficient in that sense, right? So you can see this particular standard that JTAG is using, like IEEE 1149 9.1. And one of the beauty about this particular this JTAG is the boundary scan part. Right? So what it helps is like really helps you in insert circuit debugging. So we can actually communicate with the memory and the registers part in the chip itself, right? So we can program that with the JTAG. So understanding the actual base logic for this particular JTAG is like, as we can see over here, is basically what we call as a boundary scan cell. So it is not directly going and accessing any of your the buses like high-speed bus or a peripheral bus, but it is on the boundary level. We are trying to debug those things for them. So here, if you observe that you have an input and you have output part, and in between we have this code logic. Right? So what does these things means over here is basically we have the decoder and the registers, right, where you need to decode the instructions part, as well as you have a register for the data as well as the instruction, right? So when you are programming something, right, the important thing is like if you have a data, you have a instructions over there. So when you are trying to debug things, these are the two critical important parameters that you look for, and that's what this particular architecture looks into. We'll see that in detail, how does that happen. So eventually, as it says, like it has basically those 16 different finite states machines, right? And eventually, with the help of these instructions and the data registers, it takes care of debugging your complete program. Right? So you can actually have a breakpoints, have a watch points over there, right? At what instruction you can have any of the data, right? So you can actually go single stepping and go in depth of what is there in your code. Right? So this is what the JTAG can do for you. Coming to the pins that we have, because this is something more important to us. The reason being, when you go from the security perspective, so these are the physical pins that the attacker will access, and eventually try to get the access of the credentials or some of the important data that in your microcontroller firmware. So here, let's understand those pins. So one is like, as you see, the TTT always stands for the test part, right? So it's a kind of a debug and test kind of thing over there. But again, if you look for, it is important is that we have a clock. So it's again a synchronous thing. but the clock is from your outside system, right? The outside peripheral is providing the clock. The input and the output part, again, they're dependent on the clock. And the TMS, the test mode select, how you're going to debug that, what are the modes over there. So that TMS is going to take care over there. Then there is what we have a test reset. It is written as optional. So what does that mean over there? So simply it's like when we go on resetting any kind of system, right? So here, since this particular JTAG is a what we call as the stateful protocol, it is working on the state machine, right? We can actually, without using this reset, we can still reset that particular port, right? So how does that happen? Is basically like we have the test mode select and we have this test clock, right? So these are kind of the reference, right? Test clock is the reference clock at which all we are doing the input and output over there. And eventually TMS is going to select that particular port. Now here what happens during thing is like if we are holding the state, like holding the state of TMS continuously high for 5 cycles, 5 clock cycles, then this will basically reset your complete system. So this way, the TRST is kind of an optional thing over there. Now, when we start now thinking from this perspective, if I want to hack into those kind of products which has the JTAG ports over there. So as you can see, the list of different, the processors or the controllers, they have basically these pins over there, right? So it means that they are JTAG enabled devices. So even if you go to any AVR architecture, like if you start from the very, very basic architecture of AVR, where it had like ATmega 8, ATmega 16, it did not have that particular JTAG capability. But if you go from the ATmega 38 onwards, like even if the ATmega 328P, which is generally used in the Arduino kind of stuff, right? So they have these JTAG capability over there. So as you can see in this picture, like most all of these microcontrollers has their pins available on the JTAG part. So these are something important when you are doing the hacking of the JTAG. First of all, you need to look for whether that particular chip is going to support JTAG. Of course, like with the current scenario, with the current IoT products, most of them having the either MIPS architecture or a ARM architecture, they will have this kind of JTAG enabled. But you need to look for which pins are connected to the JTAG part. Okay. Now, the supported architecture is, as you can see the list, right? So all the ARM architectures are supporting the JTAG. So whether you go for any of the Nordic semiconductors, the ST microelectronics, the other Texas, the ARM Cortex M4 series, whatever you go for, right? It has those JTAG ports available. As I spoke about the AVR part, right? So like series from the ATmega 32 has basically enabled with the JTAG part. MSP 430, which is again a 16-bit controller, it also supports JTAG, and the reconfigurable platforms like FPGA CPLD as well as they have the JTAG support, because that we have to configure over there, right? So it's not like similar to the microcontroller where you have that existing over there, but you have to configure that hardware when the designer is developing those things, right? And of course the MIPS architecture supports that. Now, when you are looking from the hacking perspective of a JTAG, right? So first of all is to understand what are the pins associated with that. So we looked into it. Now, when you are hacking off any product from the perspective, so how you will identify the JTAG? So as I said, like most of the time, the TRST pin is basically considered to be the optional. And then the 4 pin remains, right? TDI, TDO, TCLK, like the clock and the mode select. So if you observe over here, right, in one of the scenario, we have these 4 pins over there, right? And you can directly consider as a JTAG, right? So of course, there can be confusion sometimes that, okay, whether it's a UART port or a JTAG port, because in UART case, generally you will see the VCC ground, the RX and the TXP, right? So sometimes it's confusing which pin is this, but eventually we can smartly make out whether it's a JTAG or not. And if you see in the other picture over here, they have given the RST pin as well. So when you say 5 pins, of course, it makes sense that, okay, it must be the JTAG port over there. So this way, there are different ports available on a JTAG. So of course, like there is one PCB here, you can look over here, where you can clearly see the complete pins available, right? So the reset is there, the clock pin is there, the mode select, TDI, TDO, reset, every pin is available on this particular front page. So generally, if you see any particular product, you'll have a line of the debug codes where you have these 5 combinations where one of them must be the JTAG code. So this way, you first intuitively identify which pin or which port can be the JTAG, and then possibly you can do the continuity check with the JTAG pins on the microcontroller over there. But that is not possible for all the packages. So we have still challenges on that constraint, right? We'll see how to solve that problem as well. Now, let us check if like the past attacks that has happened on the JTAG, right? So here, what happens is like there is one home router on which the attacker has basically opened that completely, and it has identified the JTAG pins over here. Right? So you can see like the series of these 5-6 combinations, like the double headers with these 5-6 particular pins connected over there. Right? So it is again intuitively shows that it might be a JTAG as well, right? It can have a combination of UART and JTAG depending on what type of architecture or the product design they follow. If you still go in detail, right? So you can see this particular picture in detail and which pin was like TDO, TDI, right? So you can actually make out by scanning it properly on some of the devices. So there are certain devices that can help to scan the actual pins, right? EXPLIoT Nano is one of them. Oh, sorry, Bus Auditor is one of them. EXPLIoT Bus Auditor is one of them, which can help you do that. And eventually, what was the attack, right? Once you have access to JTAG, but what is to be done with that? So basically, this particular router had the login, right? So on when it was accessed on the UART port, right? It showed kind of a login over there, right? So but you need to access that particularly. You go to have the root shell of that, right? So how they did the attack on the JTAG and get the root shell access. So eventually, as you can see over here, that there is an open OCD tool, which is most famous for the JTAG debugging part, right? And what they have done is like they have kept the UART shell at the first open, and at the background with the open OCD and also the telnet connection, where you are sending the commands like halt and the resume, right? Which is to halt or pause some of the instructions over there, because you can go into the individual instructions and understand the contents of your register as well. So here, as you can see on the first part, this is what the setup was. And when you create they created kind of a telnet with this local host, right? And eventually you can see this was the MIPS 32 architecture, where basically you go and halt. Now, ideally, what was the thought process behind this attack is like generally you have the watchdog timer in the system, right? So whenever there are certain instructions that are not getting executed for a certain amount of time, the watchdog timer resets the whole of the system. Right? So this is whatever the job of the watchdog timer. So here the same thing happened is like what they tried to do is like having the breakpoints at instant of time, so that even the watchdog timer should not reset the whole system, because if watchdog timer has reset that, it means again you are losing the access control over the thing. So eventually, if you observe, 2 times they have put this particular halt instructions, right? And when they start doing the resume part, where they debug at the different breakpoints, eventually what happened is like they tried to get access of the busybox shell, right? So got the root shell access over there. How did that happen is like at particular instant of time, at particular watch point, they found that, okay, this will not reset, but the next instruction will certainly reset your complete system, right? And at that particular instant of time, they got an access to this busybox over there. So this is what people tried doing the attacks on the JTAG part over there. Now, looking from the different tools available in the market. So if you're kind of the enthusiast kind of thing, you can use still Arduino. It has a JTAG num kind of code which can use for the JTAG identification, but it has some challenges to identify it properly. So you need to have a lot of combinations into that to identify that particular system, right? So of course it's open source, it's available for free. Now, other tools which can help you to get an access to the JTAG is our own EXPLIoT Nano. So this EXPLIoT Nano is basically an what you call as a protocol, multiple protocol converter which supports UART, I2C, SPI, JTAG, SWD, everything. Right? So you can basically connect this device to your system, and you can get an access to the JTAG or whatever protocols that I mentioned from your particular IoT device. Right? So this is what one of the connections that I'm showing here. Right? So EXPLIoT Nano connected to our own Debug board to access the JTAG port. And the other software tools on the host side is, of course, I spoke a minute back, is about the OpenOCD, where you have that particular instructions to be executed step by step. It helps that the layer architecture for that. And not only ARM or MIPS, it also supports the FPGA and CPL, right? So we can have that single stepping over there. And it's a good tool, and it has support from many of the devices like STM, NRF. Most of the ARM Cortex, everything has been covered in those OpenOCD part. Right? So now what I'll do is like I'll be playing a couple of videos. So for the JTAG, we have 3 videos to be played. The first video will tell you how we can scan the port pins of the JTAG. Right? So understand the challenges when you're hacking any of the product from a JTAG perspective. Right? First of all, the first challenge is to identify the pins. Right? So once we identify the pins, the next challenge is how we can get access of that JTAG port. Right? So either you want to extract the firmware, or you want to have an access to any of the digital registers. So that is the second part. The third part is, even if you have got access to the firmware, you do the reverse engineering of the firmware. You possibly change some of the credentials in the firmware and put that malicious code back, reflash into the JTAG part. So for these things, we have these 3 different videos to be played, right? So the first video I'll be playing is about the scanning of the pins. Second video is about the extracting the firmware from the device, and the third will be reflashing the malicious part. Right? And once we are done with that, we'll go to the SWD part. Let me play that video. Let me know if that is visible. Is the video visible?
Yes, sir, it's visible.
Oh, yeah. So this is recorded by my colleague Shakir, right? And I'll explain what is happening. So this is our debug board, and we are going to basically attack this board itself by the JTAG. So as you can see, these are the ports at bottom. So let me just rewind, hold for a moment. So here on that particular front, we have this dual headers part. Out of this, one port is SWD, one is JTAG part. Right? So we'll try to scan the JTAG pins with our bus auditor. Now, this is our EXPLIoT bus auditor. The job of EXPLIoT bus auditor is to basically scan all the pins and tell which pin is what. Meaning, it will tell which pin is TRST, which pin is TCK, which pin is TMS, which is TDI, TD. Right? Only thing what we need is like identifying the common ground, right? Which is very easy. Right? So first of all, we'll connect the ground over there, and like after powering, like of course this now debug board and the EXPLIoT has been powered up. So the first part is connecting the ground pin, because that is a common thing that we need. And since this particular EXPLIoT bus auditor has the 16 channels, what we need now, rest of other 4 channels to be connected to the particular pin. But eventually, since the header has those 8 pins over there, what we'll do is we connect all those 8 pins on that header, just to identify which pin is actually doing what. So with those female to female connectors, you can simply connect that. So now connection has been made. Now let us identify which pin is the respective pins of the JTAG. Right? For that thing, we'll use those OpenOCD part. First of all, we have to go to the EXPLIoT, our EXPLIoT framework, which is open source, and there what we'll do is like we will scan the pins of the JTAG. In this EXPLIoT tool, we have certain plugins written for each of these protocols. like the UART, I2C, JTAG, SWD, everything. So once you have this, so if you see the list, you will see a number of plugins that we have written. And since it is specifically for bus auditor, as you can see, the JTAG scan for them. With the JTAG scan, we'll try to scan the pins. So this is kind of a bus auditor information. So device information, and let's scan the JTAG pins now. So first of all, yes, you can get some the arguments for that. Right? So what is the start? What is the stop? So what does that mean over here is like, as we are connected to those 8 channels over there, we'll scan for 0 to 8th channel. So the first command will be the starting, -s is starting. So 0 and end with 8. 8th one. And then what voltages you are working on, because the most important thing in JTAG, which I forgot to mention in the discussion, is about the voltages, because sometimes it has 1.8 volt, 3.3 volts. So here we are the auditor is working on 3.3 volts. So now, once we run this particular command, so it has basically started scanning. And it takes a certain amount of time to scan, because you have those combinations of the pins to be scanned and to decide. Right? Again, the logic is again between those boundary scale scan and the stateful machine of ones and zeros over there. So let's wait for some moment of time. Right. So here it had just passed the scan. Okay, it was kind of a field. So let so basically it's like if you don't connect it properly, you can basically pass over there. Now when you run it properly, it is again looking for the permutation combinations possible. We just run this. So the device again did up. Right. So okay, I'll just pause for a moment. So here, if you see the combinations, it has given those ID codes over there. Right? So what happens is like with the different combinations, you will see initially a different combination. At final iteration, you will get the proper one. Right. So the final one, as you can see, the TCK5, DMS6, so on and so forth. What does they refer is basically the pin number 5 on the bus auditor, where it is connected on the DIVA board, is basically the TCK. Right. So similar for other part, right? The pin number 6 from a bus auditor is connected to the TMS part, and then you can actually trace it back and see which pin is what. So this is the final thing that we have got of the combinations. So now the next part will be basically connecting the EXPLIoT nano to this particular pin numbers, right, where those bus auditor pins are connected. Right? So this is from this particular video. Let me play another video now. Let's go to dumping of the firmware. Let me pause for a moment. So now, as what we are doing is like we have already identified which pins are what from the bus auditor. Now, as you can see in the above diagram, right? So EXPLIoT Nano is basically, again, I spoke about that, is different protocol converter. So the respective pins from the EXPLIoT Nano has been now connected to the DIVA board. So let's see how we do that. So whatever now Shakir is getting connecting, that is actually in the reference to this particular what we call as a schematic. So this wiring has been done based on the schematic. So we'll connect all the pins, the ground pin, TDI, TDO, TCLK, TMS. We can actually, you know, doesn't need to basically need to connect the TRS to it. So now it has been connected. Now next job is basically to connect it to our host terminal. Let's power it, the debug board. And connect EXPLIoT Nano to our host PC, which is the screen that you can see on the upper part. Now, what we'll do is like we'll have the OpenOCD to basically access the complete the JTAG port over there, right? So here we have EXPLIoT Nano JTAG what we have written, and eventually we'll use that particular configuration file because for doing the JTAG these things debugging part, you need the config file over there. Now inside the config file, you will see the interface like FTDI that we have, and what type of source, right? So basically, since we are using this STM32, let me go back again. Yeah, pausing over there. Since we are using this STM32F4X, which is actually the control on your debug board, eventually we use those configuration files from STM32. Right. And once we have it, let's try running that. So now we'll use OpenOCD, right, and try to run this particular config file. And so initially during the testing, initially it was open. So let's kill all the processes first. Right. So once you run that, it sees that the breakpoints and the watch points over there. Right? You can see the information about the clock speed and other important, the ZTAG, right? TAP is basically test access port over there. Now, what we to do is for debugging, we'll use that telnet, right? Creating a local host on a telnet part, and from which we are going to send those halt and resume command. Basically, we are going to single stepping for that. Right? So you can see some details about the program counter and MSP part over there. Now, once we have actually done with it, again, you can do the resetting after halt. Let's resume it. Once again, halt and then resume. So basically, idea is to access the firmware. Right. So you can see all the debug requests we are doing. Now, let me pause for a moment. What we are trying to do is like, since we're going to read the flash memory content from this data, right? So here, if you observe, this is from the data sheet of STM32 F411 microcontroller, right? So if you observe in this data sheet, right, the flash memory address is from, as you can see, from this 0x800 part zeros and till FFFF part, right? So this is the address is of our interest from which we are going to read it. So what we'll do is, while reading the firmware from that, we'll put the same address. So now, as we are debugging it, we try to read the firmware from the flash memory. So this is the dump command. So we try to dump the image, read the image, and we'll store that in the host PC. So now, once you enter into it, and we have to give an address. So the starting address, as you can see, like 0x800 times 0, that will be the address. So let me just run it quickly. So if you observe that from which address are we running, right? So from 0x800 to 7FFF, and it has shown successfully we have dumped that particular byte. We dumped that particular bytes. So this was the size of the form. So this way now you have extracted the firmware from your microcontroller. Now the next part is like, we have extracted the firmware, we do some reverse engineering on the firmware, and basically accessing the password, right? Accessing the password, as well as we try to change the password in the existing the binary as well, right? So let's look into it. So here what happening is like the other tool that has been opened over here is basically the bless tool, which shows you the complete hex values of the binary that you have extracted over there. And as well as what we'll do is like strings too, right? It extracts the strings into your binaries part. So the password that will be showing over here. So you can see all the firmware extracted from this particular debug board, and eventually at particular point we have a password for that. Of course, like you need some expertise to understand which can be the password. Here for ease, we are showing what was the password. So you need to figure out from all those strings which is the password. So basically the font end space hyphen is basically the password. Now what we'll do is in our debug board, we have certain labs to access the JTAG. Eventually you have to do the reverse engineering on that and access the JTAG port. And that was the password that has been saved over there. So we are accessing now the debug board or a serial and trying to basically enter that JTAG password. So basically it's a screen command, which is not visible at the moment because of multiple screens. Now you have got the serial access to that. And if you look for the challenges, challenge number 4 is for firmware analysis. It is asking for enter the password. Now, as is the font end space %S is basically the 10 characters password. So this is what access granted over there. So this way we have got access from the reverse engineering or analysis of the firmware part. Now, the next part over here is like, as we have basically dumped this particular firmware, let me pause for a moment. As we have dumped this particular firmware over there and we want to patch it with the malicious code, right? So what we're trying to do is like in the bless tool, as where we can see that font end space, the percentage is the password over there. We'll try to replace that with the malicious, right? So let's see how does that happen. So in the screen, as you can see at the bottom, he's trying to enter the font end, that particular password over there, to search where that is actually located, right? And when you search it, it's a text, of course, right? So when you find, so it has shown this is it has highlighted where it has the password is stored. And now what you do is you replace that with something else. So what he has replaced it with backend, front end to the backend. And now the binary has been saved. So now this is not the original one. We have manipulated the binary. And once we ignore it, basically it has been saved. The next job is to basically upload that value or refresh that binary, the malicious code, into the existing microcontroller. So here we have the setup ready as we had done in the previous video itself. Now here what we'll do, instead of reading, now we'll write that through the JTAG code. Right? So now we can see the password has already been changed from front end to the back end. Now, similar to what we had done in the previous, where you open the config file and do the telnetting, we'll do the same thing. Right. Now, instead of dump, we'll flash it with this command. And for this particular matter, what we need is only the starting address. Here, write image and erase the existing one. And we are reading from which path is the actually host local machine path. So this was the binary that we have manipulated. And we are writing that to the address of 0x8004 times 0. Right? So it has actually enabled over there, right? The flash drives, everything has been done. Now what we'll do is like we'll use that same backend, the password that we had done, and try to get the access of the JTAG port from there. So it has written. Now what we'll do is we'll again get an access to the debug board. This is the password that we'll copy paste when we get an access. Let's close the JTAG part. We have done the work of that. So now we'll try to access the UART port of a debug and go to another firmware analysis lab, enter the password. This time we are just copy pasting the password like the backend. So we'll just copy, Control C, Shift Control D, and access has been granted, right? So that way we have changed the password and put a malicious code over there. So this is how you can do such kind of attacks on the JTAG, right? So either accessing this scanning of the pins, accessing the firmware from that, and reflashing over there, right? So this is about the JTAG. Now let's go to our discussion on the SWD. So not much to go into SWD because most of things, the basic concept has been covered already in the JTAG. So to understand what is there in the SWD is just one of the derivatives where we have a JTAG with n number of pins. But when you try to debug through the serial, like so serial wire debug, SWD again stands for the serial wire debug. And it is just a job of the 2 pins over here. One pin, what we call as a serial wire debug input output pin, which is a bidirectional, as well as another is a clock pin. So again, this comes as a synchronous communication over there. ARM provides those kind of bidirectional wire protocol, right? And it is basically using as a debug access port. So we have those access port and the debug access port, right? So we can have that basically daisy chain, and you can do the multiple master slave kind of stuff as well. Okay. So understanding the architecture and just smaller differentiating between JTAG and SWD. What we have seen from the previous thing about the JTAG is like you have the boundary scan associated with the JTAG, right? You scan that over there, the test logic that you're scanning over there. But when it's coming to the what you call as SWD, the other thing happens over there is like as you can see in the picture is about the AHB and APB, right? So AP is again the access point, access port, and AHB is here stands for the advanced high speed bus, which is the part of the ARM, what we call as the AMB architecture. as well as the APB is the advanced peripheral bus, right? So there are different sections of the memory or the DMA which is connected to the AHB part, and other registers and some of the peripherals are associated or connected over APB bus over there. Now with the particular SWD, we'll try to get the access of these kind of the bus part over there, right? You get an access to that particular registers inside your microcontroller, and even you can similarly you can flash or you can extract the firmware from the same port over there. Right? So this is more onto the debug side over there. And of course, it is again the master and slave communication. So when we say we have only one master and one slave, that's what we call as a debug ports. If you have multiple slave in a production level, when you have to program many of the things, right? So you have many slaves over there, and then it is termed as an access port part. Right? So these were the terms or the acronyms, what you can see. Right? So one is the JTAG that we discussed, the debug part, the debug port associated with the SWD, and the access port associated with the ZWD or JTAG as well. Now, right, so the ARM has basically kind of provided this two part over there is accessing the memory as well as the JTAG part. Right? So this is the addition from the access port for the ARM. Now, when you come into the actual working of the SWD, so you have a certain frame format for that with the 8 bits of header, right? The acknowledgement as a 3 bits and the data payload, right? Acknowledgement is much important. So if you recollect the I2C part where we need a kind of synchronous communication and the reliable communication, you need have this kind of acknowledgement over there. So similar, the acknowledgement is present into the SWD protocol. So here, if you look for the write transfer, where you can see this particular format, since we have these only tokens, the data and the clock. So the upper part is the clock, and with respect to that, we have a data. So if you look from the read and write perspective or the frame over there, so the first part is the header part, where one of the bit like AP and DP. Right? So if we set this particular bit as 0, it will act as a debug port. Otherwise, if you set it as 1, it will as an access port. That depends on what type of use cases you have. Similarly, for read and write, if you are writing, put this particular bit 0, writing bit 0, reading bit 1. And then you have an acknowledgement, right? So 100 is acknowledgement for the write transfer. And then you have this particular data bytes, like so 0 to 32 bytes of the data that you have. So this is what the writing happens over the SWD. On the other hand, when you look from the reading part, the majority part is changing this particular bit, right? R and W bit, right? So that way read and writing can happen. Now, but now there is one more thing that is associated with JTAG is the wait response stuff. Sorry, not JTAG, SWD is the wait response stuff. So eventually, when you are actually having this process and acknowledgement process, right? So when the bits 010 has been set by this particular device, 010, it means that the acknowledgement in the process, right? You are reading that data or writing that data, and that's why you are not sending whether the things are completed or not. But whatever partially you are done, you are just representing that okay, it's a wait response or an acknowledgement response from that perspective. Other than that, whenever you have faults in reading or writing, right, it has the error code for that, right? And the acknowledgement has been mentioned as 001. And this is very funny thing over here, what it is called as a sticky bits. The reason for that is called as a sticky bits, especially this fault response is like, let's say you are writing or reading something from a SWD, and if you get a fault from your host system, eventually till the time you don't clear this particular state or your particular this bits over here, right? Even if you continue doing read and write, it will still give that fault response, right? And that's why it is called the sticky bit. And this is the funny thing with the SWD part, right? So so this is what the basics of the SWD. Now I'll explain one of the attacks that has happened in the past on a SWD. So here is basically the Nordic Semiconductors chip, NRF 51822, right? And as you can see, this possibly can be a kind of a BLE beacon or some kind of BLE device used in a consumer thing, where you can see actually you have a battery operated device, the low power battery BLE devices over there. And from this perspective, we can see in this pin like SWDION serial the SWD clock over there, right? So once you have this identified this clock, you can actually tamper about those things and try to extract either a firmware or access to the deeper registers of your system board. Right? So what they had done is like, you have those Seger debugger, right? So it works with the SWD and JTAG part. And they had connected this SWD to that particular tag or BLE beacon over there. And eventually they got access to the complete register set inside your microcontroller. And not only that, in the bottom part, as you can see, the where the firmware, they have extracted the firmware from starting to end. So you can see the start and the end address for them. So this way you can actually extract the firmware from that. Right? Typically what happens when you have this kind of devices, the production guys have this debugger and they try to program that that particular chip through this particular debugger. But eventually the same thing can be reversed, where attacker has those debugger with them and try to extract the firmware from your device. So the possible attacks with the SWD are either you get access to internal memory and the register access, right? Extract the firmware, similarly flashing back the firmware as well, right? Or you can do the debugging over there. Now what we'll do is like, we have one small video associated with the SWD where we'll simply scan, similar to JTAG, we'll scan the pins with the SWD and we'll show that. So this is what we have. Right. So now it is a similar setup what we have, where you have a bus auditor, and now instead of JTAG, we are scanning for the SWD. Now first you connect the ground, and remaining other pins associated with that. Again, you have those 8 header pins. As it's a whole header, we need to scan. You can also use those things together, so you can connect all the 16 pins and eventually you can scan as well. But just for the ease, we have shown that as a separate what you call a separate practice or separate exercise to know you better how we can go for, especially for SWD or the JTAG part. So now we are done with the circuit. Let's power it up. So now the device is powered up. What we'll do again is go to our EXPLIoT tool. And this time I will try to run the plugins for the SWD scan. So you can see SWD scan. So again, the commands are similar. That's starting 0th channel and ending with the 8th one with the voltage 3.3. Right. And as you can see, we have identified the pins over there, right? So we can see the serial SWD clock, pin number 2, meaning the bus auditor, the pin number 2 of the bus auditor where it is connecting is actually the SWD of the microcontroller that is connected over there. And similar with the pin number 0 of the bus auditor where it is connected on the board is the pin associated with the SWD IO. So this way we can actually find out the pins. So that's it from my side. Right now we can have a Q&As.
Thank you so much, Mr. Yashodhan, for this wonderful session. Let's just check our chat box to see if we have any doubts. Hmm. Yes. So the first question is, let me just share my screen. So, Mr. Abu Bakr Siddiq is asking if you can name the board, please.
Okay, the board names are, I can put in a chat box, is like EXPLIoT Nano, and okay, the board was EXPLIoT Diva board, right? And other board like EXPLIoT Nano and EXPLIoT bus audit. So on which we are doing those attacks, that was the Diva board. The Nano was used to extract the firmware or write the flashing part over there, and bus auditor is used for scanning of the bus.
So this was one question which was asked during your first video. The Chetan is asking if you connected to another set of pins.
I didn't get, where is it?
This one, sir.
I didn't get the question.
Chetan, can you please ask the question again? We can move on to another question. What's the main microcontroller used in the EXPLIoT Nano board?
Okay, it's STM32 F4.
Is this performed using EXPLIoT Nano?
Attacks, yes, we have done that with EXPLIoT.
How to hide JTAG
Okay.
SWD pins? Yeah.
Okay, so one thing is like hiding on a PCB is different case, and hiding from a firmware is a different case. Okay. So generally, what happens in ARM architecture, you have some of the credentials. I just recollecting that particular term for that, but eventually, what you can do is like there is a, I'm just forgetting that particular term, but eventually you can, yeah, it's called as a RDP level, right? There are different readout protection level. So generally your microcontroller is in the RDP level 0, where you have access to all your UART and JTAG port over there. Eventually, let's say if you put to RDP level 1, what will happen is like you won't have a read access to the port like UART or JTAG or SWD for that matter. That way you can do these things, right? But eventually, if you regress back from level 1 to again level back 0, right, you have to erase everything, right? So that otherwise it won't be possible. Other way is like if you want to make it permanently, you go to RDP level 2, but eventually you cannot regress back to any of the level. Then your microcontroller is kind of the OTP stuff over there. So that way you can make our life harder.
Okay. So there's this one more question from Sayed Anwarullah, that can the Nano board be used with Windows also, or is it specific to
Yeah, I got the question. Yeah. So eventually what you can do is like you can still use with the Windows. What we have displayed is like we have our EXPLIoT framework, and those things like you can have a VM and you can use that over there. But EXPLIoT now we can use for any of the operating system. There is no issue with that.
This another question is from Harsh. In case we mess up flashing the firmware, can we reset Diva board to its default configurations?
Yeah, you can do that.
And what is the difference between Bus Pirate and OCD board?
Bus Pirate and the OCD board? Which OCD board you are referring to? I don't know what OCD board, but Bus Pirate is like again it's kind of a different thing and a different protocol. So Bus Pirate has a limitation on different I believe so, I2C and SPI, I believe so. But here, bus auditor is giving all the configuration like SPI, I2C, JTAG and SWD part.
So everyone, if you have more questions, feel free to ask that questions on our social handles. This recording will be shared in our social channels. So please follow all the social media. The link is in the chat box. And thank you all for joining us. Stay tuned and we'll see you in the next webinar. Thank you, everyone.
Thank you, everyone. Bye.